me here. I'm very happy to be here this year. I try to be reasonably quick, not to steal time to the lunch. This presentation is about LICIACube autonomous navigation software. I will quickly go through the LICIACube mission overview just to tell you what it was. Then we'll go in detail about the autonomous navigation system, the validation and optimization phase, and then finally some of the mission results. So talking about the LICIACube mission, so basically we were the tiny one in the DART mission. Of course, I think we are the less famous of the two, but okay, as you know, of course, DART main goal was to impact the Dimorphos asteroid to study the deflection, and we were there to take significant pictures of the impact and of the ejecta plume coming out from the asteroid. So this was the team composing the mission. I will not spend much time on the left part of the slide, of course, but from our side, we from Argotec were the prime contractors for the mission, which was sponsored by the Italian Space Agency. And together with us, there were also additional entities like JPL, University of Bologna, and Polytechnic of Milano, for all related to flight trajectory design, radio navigation, orbit determination, and so on. And also the Italian National Astrophysics Institute was involved for the scientific part of the mission. The mission has been accomplished using our own platform. It was a 6U platform, provided of our own onboard computer, which was running RTEM's operating system. So maybe I will add to the list of the mission taking advantage of RTEM's. And it was provided also of a cold gas propulsion system for the trajectory correction maneuvers, an ADCS with reaction wheels and RCS control systems. From the electrical part, we had solar panels and battery, of course, X-band transponder, and two optical payloads, one with a narrower field of view used mainly for the navigation pictures, so the visual navigation data, and a secondary one used mainly for shooting scientific pictures to the asteroid. So as I quickly already introduced, the mission primary goals were to capture the images of the DART impact with the asteroid, and in particular maybe of the ejecta plume, so of all the debris coming out from the asteroid after the impact. And possibly also we would like to take pictures of the non-impact hemisphere of Dimorphos, which was the one we couldn't see from the live stream from DART. This is the mission profile. So the launch has happened in November 2021. We had a 10-month cruise phase where LICIACube was stowed inside its dispenser attached to one of DART's side panels. And then after these 10 months, we have been deployed about 15 days before the impact with Dimorphos. And we started the commissioning phase, so all the preparation to the science phase, which in the end lasted only 5 minutes because, as we will see shortly, we had a very high speed relative to the asteroid. And then after that, we had more or less 6 months of time during which we downloaded all the data using the Deep Space Network. So which were the main challenges and also the main drivers for the navigation software development? So in the top right corner, there is a simple scheme showing how the mission behaves. So we had an approach to the asteroid, passing by it, and we wanted to stare at the asteroid for the whole duration of the flyby. And this could not happen with real-time commanding, of course, because being at 11 million kilometers from the Earth, we could not wait for command delivery and confirmation, which took at least 70 seconds. Also, maybe the main challenge here is that, of course, the DART mission profile was not designed to gently approach the asteroid. And so at this closest approach, we had this nice relative velocity of about 7 kilometers per second at only 50 kilometer of distance from the asteroid. And this translates to a body rate on the satellite attitude of up to 10 degrees per second in order to continuously look at the asteroids during the flyby. As a last point, there were also trajectory uncertainties. Of course, the orbit determination team worked hard to keep these uncertainties as low as possible, but in the end, the distance at the closest approach could vary between 35 to 65 kilometers, so a relatively big uncertainty. And also the timestamp of the closest approach could be affected by a few seconds skew. And so in the end, the attitude profile, which we see in the low right corner, was more similar to this one, actually. So a family of many curves affected by both spatial and time shifts. And so this required to develop an adaptive attitude control solution which could not rely on a single preloaded trajectory definition. So all these drivers were used to design the autonomous navigation system. This system is composed by many blocks working in a closed-loop way, and all these blocks are integrated in the main satellite flight control software, which worked, as I said before, on a real-time operating system, or TEMS, in a hard-scheduled way. So going in order through the blocks, we have the payloads to acquire the images. Picture data is fed into the imaging system, which detects the targets and provide the features to the following blocks. We have a trajectory recognition block, which we'll show you later, and was used to try to understand on which of the multiple possible trajectories the satellite was on. The tracking loop used to keep the attitude in such a way to always stare at the asteroids. And then the attitude controller combined with the actual attitude determination and control system to perform the reaction wheel actuation and control the attitude. So starting from the imaging system, the goal of this part of the system was to take the pictures and try to get features about the possible targets inside them. So using a pipeline with filtering to remove background noise, binarization to reduce the amount of data. Then we had object detection and feature extraction, whose final target was to get from the picture information about the position of the asteroids relative to the picture frame, and also their characteristics in terms of dimensions and dispersion of the pixels. So this was quite an expensive task if we implemented it all in software side, because our onboard computer is equipped with a GR712 processor, which, as we saw yesterday in one of the presentation, is not really a high-performance processor, even if it is very reliable. So in order to to meet the requirement requesting that each navigation loop should be executed in less than 6 seconds, and this was required in order to be able to actually look at the asteroids during the faster part of the flyby, we had to go with an hybrid software and hardware implementation, where we exploited the presence of an FPGA from Microchip, an RTG4 FPGA on our onboard computer. And so we put on the FPGA the main, let's say, time-consuming tasks, the one related with the pixel scanning and convolutions, for example, binning, low-pass filtering, and binarization of the pixel, while the software had the role to extract the features from the preprocessed data from the FPGA. And in such a way, we were able to execute all this pipeline in less than 1 second, leaving enough time for the subsequent blocks. And also, even more importantly, maybe to leave enough time for the storage of the pictures, because for each loop of navigation lasting 6 seconds, we had to store 4 pictures from the navigation payload and up to 9 from the secondary payload. The next block is the trajectory recognition block. So this one is the one in charge to detect the actual trajectory of the satellite. It would have been much easier if we perfectly know which trajectory the satellite was on, because at that point it was only required to say the satellite, okay, this is the trajectory, follow it, like in a preloaded way. But of course, this was not possible because of uncertainties. And so this block has the role to resolve distance and time uncertainties on the trajectory. And it does so using the information coming from the pictures. So in the first part of the flyby, this block does nothing but to collect information about how the target moves inside the picture while the satellite is approaching the asteroids. And at some point, like 30 seconds before the closest approach, it injects its solution into the tracking loop, which is the subsequent block, telling it, okay, this is the estimated correct trajectory we are on at this point. So the block is this one in the red square, injecting its output in the tracking loop. Sorry. Then we have the tracking loop, whose main role is to follow the trajectory on which the satellite is on in order to stare at the asteroids. If you think about the family of trajectories we've seen before, okay, they're actually an output of a mathematical equation with some trigonometric functions. But in the end, if we exclude the peak, it is mostly like a parabolic, a sum of parabolic curves. And an ideal way we found to follow this kind of curve is to actually think about it as we were following the phase of a signal in time. And so we accomplished that by implementing a phase-locked loop, and in particular a second order phase-locked loop, in order to be able to track a parabolic trend on this trajectory, and also to recover from linearly increasing errors. One additional thing this block does is actually to perform a final fine-tuning on the attitude of the satellite based on the position of the asteroids inside the picture. So the goal, of course, is to have them as close as possible to the center of the picture in order to maximize the likelihood to keep the asteroids inside the picture for the whole time. The output of this block is a desired attitude solution, which is fed into the attitude controller, which actually is mainly composed by a PID controller with like a special features that the gains of the PID controller are not constant parameters, but depends on the actual trajectory of the satellite. So when the trajectory recognition block estimates one of the trajectory from the preloaded family curve, the gains of the PID are updated accordingly in order to use the best option possible. So now a quick look at the validation and optimization phase. So not surprisingly, we went through a first validation at unit level, followed by a system level validation. During the unit level validation, we tried to verify the functionality of each of the blocks independently. And so, for example, we tested the imaging subsystem block using a software test bench. We tested the trajectory recognition and tracking loops, extracting many curves with Monte Carlo simulation. And we tested the attitude control block using MATLAB and Simulink. And after that phase, we went for the validation at system level. So all the system has been integrated. before at software simulated level and then on the real hardware. And we used a high resolution image generator to provide the pictures to the image tracking loop. And in the end, we completed the validation with a hardware in the loop setup, sorry. In order to generate the pictures, we took advantage of a tool developed and maintained by the European Space Agency, which is called Pangu. And Pangu is actually an environment simulator, so it can perform 3D rendering of objects and scenes, but has two key features which were particularly useful for this phase of the validation. The first one is that it allows to also set trajectories and relative position between celestial bodies, like for example the two asteroids and the simulated satellite. And the second one is that it allows also to model the parameters of the camera you use to extract the pictures. So in this way, we could inject the characteristics of the CMOS sensor of our cameras in order to have images as realistic as possible from the simulator. Using this simulator, we implemented a fully software implementation of the system, mainly using MATLAB, but also with some custom software development. And this was used to generate a lot of possible initial conditions to be fed to the autonomous navigation system to see how it behaved starting with different conditions. And this was done mainly for because we had two main key performance indicators for the system. The first one is that on a nominal trajectory, we had to have pictures for the 98% of the flyby. And over that, in non-nominal conditions, we had to get by analysis that the system would have been able in the 75% of the possible trajectories to have the targets in the pictures for at least the 75% of the time. So it's quite tricky, I know, but it's in the end to maximize the likelihood to have the asteroid in the field of view for the maximum time possible. And as such, we went through an optimization phase using the software implementation, which allowed us to execute the simulation as fast as possible instead of waiting for the real timings on the hardware. And using this optimization phase with genetic algorithms, we've been able to improve a lot the system. So, for example, looking at the plots on the right side, we passed from only 14% of the simulation run having the asteroids inside the pictures for all the time to 58%. The final step was the complete hardware in the loop setup. So instead of the simulated version of the software, we added the real onboard computer running the flight software. And the images were still generated using Pangu, using the graphical simulator, but they were injected into the OBC using the actual spaceware interface used also by the payload on the satellite. And also the attitude control and the dynamics were simulated by the real hardware and a validated dynamics simulator. So the outcome of this phase is we were able to perform this kind of run of simulations where we performed the flyby of the asteroid with simulated pictures, of course, but this was required, of course, to validate and optimize the setup. And then very quickly, some of the flight results. So first of all, what we did during the commissioning phase to calibrate the system and prepare it as best as possible. So we performed the first payload calibration. So we took pictures of known targets, for example, the Earth, the Pleiades constellation, and Jupiter, to understand which parameters we have to use to acquire the pictures, for example, the gain, integration time, and so on. Also, we performed an attitude calibration phase where, using also known objects, we fine-tuned the alignment between the cameras and the attitude control system reference frame. And just before the flyby, we performed, let's say, a fake flyby with no target, so a couple of days before the actual approach to the asteroid. And this was useful to have real-life measurement of inertias, of how the applied torques had effect on the attitude of the satellite, and so on. Using all the data we gathered, we ran a new run of optimization on ground using the software in the loop setup. And so in this way, we were able to update a final version of the gains of the parameters and of the expected nominal trajectory after the orbit determination phase. So I reported a couple of pictures. You will forgive me if they are not of super high quality, but for example, the first one on the left is the first picture we get when we started the science mode, and the Dimorphos asteroid is actually barely visible, but it becomes really visible after DART arrived on the middle picture, and also you can see the plume expanding on the right one picture. Then some other pictures we got. This one was one from the scientific payload while we were approaching. This one was while we were flying over the two asteroids. And this one is a nice stack up, I think someone on Twitter does. This time lapse I put in the slide just to show that actually the system has been able to track the asteroid and to perform the navigation, even if, as you saw, for a couple of navigation loops, we had lost the target inside the primary navigation camera. But this was one of the reasons we also had a secondary camera with a little bit wider field of view, which was able to get the pictures for the whole time. So just to recap, this is not really meaningful, but we were already happy to have the satellite on and alive after that 10 months frozen deep space cruise. The autonomous navigation system, as we saw, had performed quite good, and we were able to shoot 627 pictures during the flyby, which we've been also able to download to ground, thanks also to the Deep Space Network. And the main goal to release the pictures of the ejecta plume and of the impact has been reached, so we are very happy with that. Thank you very much, and I'll be happy to take any questions.